Today, we're going to start to tie together some of the things we've been talking about in the last few sections. As you begin this video, you may want to pause it right here and copy down these two theorems, and then come back and listen after you've already written them down. So once you've unpaused it, what we're going to talk about is the idea of this fundamental theorem of algebra. We're not going to go into proving the fundamental theorem of algebra, but it's going to come in very handy for some of the other things we're going to do in this text. What you need to know about this theorem is the idea that if we have some polynomial p of degree n, so remember that might be something like 3x cubed plus 2x squared minus 9. So this would be of degree 3 here, and it would have a leading coefficient of 3. And if that degree is greater than or equal to 1, then what we know is that this polynomial p has at least one 0. And what we mean by that is that if we set this polynomial equal to 0, there is at least one x that's going to make this true. Please note that this may not be a real solution. It could be an imaginary solution. But this fundamental theorem of algebra then leads us into a theorem that helps us to summarize the last three sections that you've looked at. And what it tells us is that theoretically, we can completely factor any polynomial. And that theorem is the linear factors theorem. What the linear factors theorem says, if we take this polynomial, and remember this is the generic way of writing that polynomial, where its degree is greater than or equal to 1, and this leading coefficient is not 0, then we can factor the polynomial into these individual linear factors. So in other words, it might come out to be something like this. What you also have to recognize is these constants, again, may or may not be real. They could be imaginary numbers, and they can repeat. So you could have something like 3 times x minus 2 times x minus 2, and it's a factor that occurs twice. Let's look at why this is true. So we are going to prove this theorem. Let's assume that this generic polynomial p of x has at least one real 0, or at least one 0. It doesn't have to be real. We know this is true from that fundamental theorem of algebra that we're not proving, but we're going to call this 0 C1. So using division, we know that x minus C1 is a factor. And when we do long division, we can rewrite p of x as that factor, x minus C1, times whatever that quotient is. We also know from our study of long division that that q sub 1 of x, that polynomial quotient that's left, has a degree of n minus 1. So if the degree of the original polynomial was 3, then we know that this quotient has a degree of 2. Notice that this quotient is still going to have a leading coefficient of a sub n, since that x minus c sub 1 has a coefficient of 1. So note, this is 1, so we know the coefficient here is still that same a sub n. Now, if that quotient is equal to 0, in other words, that means that the degree is 1, then we know that q sub 1 of x is equal to a sub 1. And we know that p of x can then be written as just a sub 1 times x minus c sub 1. Otherwise, then we can conclude that q sub 1 of x has degree of 1 or higher, And by the fundamental theorem of algebra, it has a 0. We will call C sub 2. So now we can take P of X and we can write it as X minus C of 1, this new factor X minus C sub 2, and then the quotient that's left there. Note Q sub 2 has a degree of n minus 2 and a leading coefficient of a sub n. And we can keep doing this over and over and over n times until we end up with P of X is a sub n times X minus C sub 1, X minus C sub 2, all the way down to X minus C sub n. Now this linear factors theorem does not tell us a couple of things. It does not tell us that it has all real zeros. Some of them could be complex. And it also does not tell us that there are distinct zeros, that there are n of those. Some of them could be repeated, as we mentioned earlier. But it does tell us that the polynomial can be written as linear factors, but it doesn't tell us how to get them. One other thing we can get from this theorem is we can see that the graph is going to cross at most n times on the x-axis, and it's going to have at most n minus 1 turning points. So a graph will cross the x-axis at most n times and have at most n minus 1 turning points. And by that, we just mean where it goes from increasing to decreasing. So what that means is if I have something like x to the 4th minus 2x cubed plus 1, if I draw a rough graph of that, it looks something like this. And notice it crosses 2 places. So it has at most 4 places that it crosses. It only has 2. And notice that it also has only 1 turning point, because here it's decreasing, 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 increasing. It only changes direction once. Whereas if you have something like this, perhaps you have x cubed minus 2x squared minus x plus 1. It's going to look something like this. It has 3 places that it crosses, at most 3, and it has 2 turning points. Turns to decreasing, turns to increasing. So it has 2 places that it changes direction.